You have today some other classes? Do you have some other classes today?
Yes, sir. At evening, I think.
Yes, sir.
Time? Evening. When?
Evening, sir.
Evening.
Okay, okay. Right, so I will start now. This screen is visible?
Yes, sir.
Okay. So these are the fourth unit, fourth module, feature extraction methods. So we are discussing that dimensional reduction methods in fourth module 4 in your introduction to machine learning subject. So the introduction to machine learning, that the module 4 is dimensionality reduction techniques. So in the dimensionality reduction techniques, generally we start with feature selection and feature extraction. There are two various methods for reducing the dimensions in a given data set or of a given application. So here initially we have seen the very first class, we have discussed about that feature selection. So that in the feature selection, we have discussed so many concepts. So there's the main thing we have discussed is subset selection. So forward subset selection, backward subset selection, hybrid subset selection. So then we move on to the feature generation methods, that is feature extraction methods. In the feature extraction methods, this is a slide which I have shown you in the first class itself. So these are the different methods which are available in feature extraction methods. That will be there will be six methods in your syllabus, in your syllabus in your module 4. So that syllabus, you can see that the principal component analysis, that is one of the method. So another one is the linear discriminant analysis. Another one is another methods are called factor analysis and multi-dimensional scaling. So and then another two methods are called as isometric feature mapping, locally linear embedding. So these are the different methods. So if you see these methods, we have discussed some of the methods here, right? Almost we have discussed some of the main methods already. So you can see that the principal component analysis we have discussed. This is one of the linear projection method. It is one of the linear projection method, but it is an unsupervised method that we have discussed in the earlier. Another method we have discussed is called a factor analysis. That is also a linear projection method. That is also unsupervised method that we have discussed. Now today we are going to see the linear discriminant analysis. That is one of the feature extraction methods, but that comes under supervised method. So already you know what is the difference between supervised and unsupervised. In the first module, in the first class, some one or two classes, I will discuss what is supervised and unsupervised. The same meaning will be here also. So there is no difference between that meaning and now. So if you see this, there will be a supervised and unsupervised, same thing. So that in supervised methods, there will be a linear discriminant analysis. Another one, the remaining three methods are unsupervised. So that is a principal component analysis and factor analysis that we have discussed. Another one is multi-dimensional scaling that I will discuss in tomorrow class. That's a small topic only. I will not go in detail in multi-dimensional scaling, but linear discriminant analysis, I will go a little bit detail. So that multi-dimensional scaling, these are the methods. Already I gave the assignment and seminar for these two topics, that is isomap and locally linear embedding. So when you are preparing this isomap and locally linear embedding, that time you will understand what is the difficult of these concepts. So when you are preparing for writing for assignment and when you are preparing for seminar, that time you will definitely understand what are the difficulties involved in these type of topics. Right. So for making you people to understand easy and simple manner only, for that only I am explaining these topics in very detail, in different ways also. So if you go and prepare for isomap and LLE, that time you will understand definitely. So now we go for that linear discriminant analysis. So this linear discriminant analysis and the PCA, that is a principal common analysis, these both techniques are almost look like similar, but there will be a big difference between these two methods that I will explain. Okay, clear. So next we move to that. I will close this lecture, PPT, then I will take that one. So this is the dimensional reduction techniques, linear discriminant analysis. So linear discriminant analysis. Now the screen is visible.
Yes, sir.
Yes, sir.
Okay. Linear discriminant analysis is, as its name suggests, is a linear model. So the first thing you should be very clear that the linearity and non-linearity, that is a basic difference. That is basic concepts difference. So that you have already know that. So because so many places we have discussed this linear and non-linear. So now this linear discriminant analysis is also one of the linear model for classification and dimensional reduction. So here actually in linear discriminant analysis, so most commonly used for feature extraction. So mainly it will be used in pattern recognition, pattern classification, that type of problem we go for a linear discriminant analysis. So it's not a new concept. It will be it has been used for a quite long time. So first in 1936, the name of the mathematician is called as Fisher. He formulated the linear discriminant for two classes, and for only for two classes he defined the function, discriminant function. Then later on in 1948, the name of the person is called C.R. Rao. He generalized it for a multiple classes, not for a two classes. He increased the number of classes and classifying using this linear discriminant function. So normally what that linear discriminant analysis, actually linear discriminant function is doing is, it projects the data from a d-dimensional feature space down to a d-dash or d colon something. We can go for some other name k also. So here initially the d-dimensional feature space considering high number of dimensions. So for example, it may be consists of 100 number of dimensions. So it will be projecting this data to the d dash, that is a lower dimensional phase. So that is a lower dimensional phase that will be consist of only 10 or 20 dimensions. So we are projecting the 100 number of dimensions to a 10 number of dimensions. So this is similar to PCA. What PCA did, the PCA did the same thing. So PCA, what we did is, so the same thing. What we did is the projection of the number of large number of high number of dimensional features into a low dimensional space. So already in that time I have explained you, there will be a d number of dimensions. We are projecting into the k dimensional space. K is less than d. Similarly here we are putting d dash. So the d is greater than d dash. That is original dimensional space feature spaces. The number of dimensions is high comparing to the new one. So we want to project the 100 number of dimension to a 10 number of dimension space. So that is same thing we have did in PCA, but in the concept is different in PCA and linear discriminant analysis. So what we did is in PCA, we don't know about the, so before go to that, I will go some basics of that. So why we need a linear discriminant analysis? Before I enter into that, difference between LDA and PCA, that is a big difference in PCA and LDA. So before I go to the difference between PCA and LDA, so I will show you what are the reasons we go for a LDA, linear discriminant analysis. So in a classification, already I have in the module 3 and module 2, so I have discussed some of the classifiers. That is naive bias classifier, multinomial bias classifier, and different type of classifiers I have discussed. So in that classifier, there is another one classifier, is the important classifier that is not available in your syllabus. So that I did not discuss that topic. So that is called as logistic regression. The logistic regression, it is the name is like a regression, but it is not like a linear regression or multiple linear regression. So it will be used for a classifying purpose. It is not used for a regression purpose. The logistic regression is the name only, it will be having a regression, but it actual purpose for this algorithm, logistic regression or this model, logistic regression model is the purpose of classifying the different classes, not for a regression purpose, right? So in logistic regression, what we are doing is we are classifying the models. So it will be well performed, that logistic regression. So, but it will be good for binary classifications. So either the class will be two classes, 0 or 1, so or a male or female, or the different two classes. The two classes, it will be okay. Logistic regression performance is good. But nowadays, there will be a multiple classes also. We are using logistic regression in so many places. But comparing when we go for a multiple class problems, so that time that the linear discriminant analysis is some better than the performance of the linear discriminant analysis, better than logistic regression. That is important. So the logistic regression, so that you did not study in your syllabus machine learning model this semester. So actually this is important algorithm. Just you can explore through that our materials available in the internet. So there's logistic regression actually doing the task of classification. But here what we are doing is we are classifying for 2 classes. The performance is perform well. But when we go for multiple class classification, that time this logistic regression not doing well. But even though some of the applications in multiple class classifications, we are prefer logistic regression comparing to linear discriminant analysis. But why then? What is the purpose of LDA? So the LDA purpose is not only for classification; it will be also doing the purpose of dimensionality reduction. So, but in logistic regression, we will not reduce any dimensions and all. So, in logistic regression nowadays also some main applications they are using logistic regression. But in LDA, what happens is LDA we can reduce the dimension. Also, we can do the classification. Both thing we can achieve using this LDA, linear discriminant analysis. Right. So at the same time, it will be one of the data pre-processing technique. LDA is one of the data pre-processing technique, as well as it will be act as a machine learning classification algorithm. So the LDA, but in logistic regression, we are only doing the classification. So it is like a linear regression or multiple linear regression. Then you can ask why the name will be called as regression. So actually, regression in linear regression or multiple regression, what we are doing is we are getting the input, we are predicting the output. But in the input is a continuous variable, output also a continuous variable. That in regression, linear regression and multiple linear regression. In simple linear regression, we are having only one input variable, or we can go out predicting the output. In multiple linear regression, we are having multiple input variable, we are predicting the output. But in logistic regression, what we are doing is we are having the input as a continuous variable, but our output is a categorical variable. Our output is a classification. So here output is a 0 or 1, that type of whether the person is having cancer or not. So whether the account holder, the customer is a malicious customer or not. These type of things we are defining in output. Here not we are predicting the continuous output variable in that logistic regression. So in classification, actually in classification, what we are doing? In classification also, we are doing the same things. We are classifying the things. But in logistic regression, we are giving the input as a continuous variable. We are getting the output as a classification. That is a different categories, categorical variable. But in linear regression and multiple linear regression, what we are doing is our input is also a continuous variable. Output is also a continuous variable. So we are predicting the continuous variable, right? So that is the difference between logistic regression and linear regression and multiple linear regression. So when you come to the logistic regression, the comparing to LDA, linear discriminant analysis, this logistic regression is actually doing well in binary classes process classifications. That is the only two classes are available. We can do better in logistic regression. But in LDA, it can be used for multiple classes. But at the same time, we can use a number of applications. The logistic regression used for a multiple class application also. But moreover, the advantage in LDA is LDA not only do the classification process, it also do the dimensionality reduction. So we can reduce the dimension using LDA, but we cannot reduce the dimension using logistic regression. So in some certain cases, if we want to reduce the dimensions of our data set or our application, and we do a classification, that time the people will go for a LDA. So because LDA can projecting our higher dimensional feature space to a lower dimensional feature space. At the same time, the classification property will not affect using LDA. Then we go for a PCA. Why then what is the problem with PCA? So we can using the same concept in PCA. What we are doing is we are reducing the dimensions of a given data set, higher dimensional space. That is given data will be in the higher dimensional feature space. We are projecting the higher dimensional feature space into a lower dimensional feature space using PCA. But in LDA also the same thing we are doing, but what is the difference? I will tell. Wait. So the LDA is also used in face detection algorithms. So some of the applications are available in LDA. So there will be another one application is called a Fisher faces LDA. So it is used to extract useful data from different faces. This is already available one thing. So some of the shortcomings of LDA. So what are the shortcomings of LDA? Is it will be only applicable for linear decision boundaries. It will not be good for a non-linear separable classes. Actually, in real time, we cannot expect all the data will be a linear separable. So there will be also a non-linearity also available in that real time. So that non-linearly separable classes, it will not be work well, LDA. So that time it will be LDA will be having somewhat problem. So similarly, another one problem we are called as small sample size problem. So you will not go into detail in these things, but anyway, you can keep in your mind these are the shortcomings of LDA. Some of the areas we cannot apply this LDA. Where the number of observations, that is number of instances, exceeds the number of features. that LDA might not perform as desired. This is called as small sample size problem. That is a regularization required, right? So that is another problem. Another one thing. So actually, this is the statement is wrong. Actually, the number of features exceeds the number of observations. So there is a number of features is more, but the number of observation is less. That is called a small sample size. Okay, that is a regularization required that time. So that time also the LDA will not be good. Another one. So already I was till now what I tell you, what is linear discriminant analysis, why we go for a linear discriminant analysis, then what are the shortcomings of the linear discriminant analysis, then what are the assumptions we have to make before applying LDA to the particular scenario. So we are assuming the data to be distributed normal. Already you know what is normal or Gaussian distribution. So Gaussian distribution of data points. So usually the Gaussian distribution will be look like a bell-shaped curve, right? So it will be look like a bell-shaped curve. So each of the classes has identical covariance matrices in a Gaussian distribution. So, but in some cases, in real time, so there will be a LDA quite perform well, even though the assumptions are violated. Even though the assumptions are violated, the LDA perform well. So already that have been proved. But before getting to the LDA, we have to take assumption our all data points. Assume that all the data points distributed are normally or Gaussian distribution of data points. I think you know what is normal or Gaussian distribution because already I have explained it in module 2 and module 3. Because in module 2 and module 3, most of the time we have spent with this normal and Gaussian distribution of the data points. So that will be like a bell-shaped curve. Okay. So the main condition of this will be each of the classes have identical covariance matrix. So this also we have discussed in module 3. We have taken different cases, right? Case 1, we are taking identical covariances matrix. Case 2, we are taking different covariance matrix for different classes. Similarly, we have equal covariance matrix. So similarly, we have taken different assumptions and we have solved that, we have derived that what is the nature of the particular normal or Gaussian distribution in that module 3, right? So now onwards we are jump into the concept of LDA. So till now that will be the introduction portion. So now we are enter into the LDA. So what do you understand from this diagram? Anyone can say?
So classification is not happening.
Yes, very good. So here what we are doing is before we are applying PCA. This is PCA. In that PCA, we are applying this algorithm. Algorithm PCA, principal common analysis. We are applying this data. The data is in the left-hand side. That is the x-axis, y-axis. It having 2 points, two coordinates. So the green color square and red color circle. These are the two different classes. So before applying PCA, it will be having the classified. It will be separated. So we can say this green color will be either person having a cancer, having a tumor or malignant. So this type of the classification already we defined. So our data will be have the property of classification property. So the red color circles, all the 6 data points belong to one class. The green color square, so that all belong to another one class. So these two calls are separated in our data. But when we applying PCA, what happened? After PCA, we reduce the dimension, 2 dimension to 1 dimension. So you can see that in the left-hand side, we are having 2 dimension, x-axis and y-axis. When we are applying PCA, we change into a PC1 axis. So we will get PC1 and PC2 from that concept of largest eigenvalue corresponding to largest eigenvalue, which is the PC1. That space is taken as a PC1. That PC1 we are keeping. Another one PC1, another one PC, we can neglect that. That we will learn in principal common analysis. So here there will be a 2 axis. So we can calculate or we can generate 2 PC axes, PC1 and PC2. We can neglect PC2. Otherwise, we can take the PC of which large eigenvalue is the largest one among the 2. So that will be the single axis. So I am showing the x-axis like this. So here what happened is, so these all the classes are overlapping each other. So now we cannot separate this. Now, due to what happened applying PCA, we got the advantage of reducing the 2 dimension to 1 dimension. That is okay. That is our purpose satisfied. We reduce the dimension from 2D to 1D. But what problem arises here is, so we lost our classification property in our data. So now we cannot, using this single dimension, we cannot classify our data. So before applying PCA, our data is a very good classification property. So, but due to the application of PCA on our data set, so we lost the classification property of our data. So now it will not be useful for us because we need a separate classes. PCA does not bother about the data points property. whether the data points belonging to that particular class or whether the data points belonging to that class, that will not be considered by the PCA. PCA, in general, we are applying PCA to the data set. So the data will be projected to the single dimension, but here what happened? All the data are overlap each other. So this is the main drawback of PCA. See, even though n number of dimension, we can project into the d dimension of originally there will be 100 dimension. We are projecting into a 10 dimension. So that time that 100 dimension data projected into a 10 dimension data. So that PCA does not bother about the property of these 100 dimensions. So even though sometimes before applying PCA, we can have the different classes. There will be 10 different classes are there among the 100 dimensions. But after projecting into a 10 dimension, the 10 different classes will hide. So due to the problem of due to the application of this PCA on that particular data set. So, but LDA, what happens? So you can see this. This one is the left hand side diagram is a PCA. The right hand side diagram is a LDA. You can see the difference between these two. Can you find out the difference? What is the difference between these two diagrams? What do you think about these two diagrams? The difference between these two diagrams? The two diagrams, both two axes are there, one blue color line are there. What is this? Linear discriminant analysis. Can you say what is the difference between? I already informed you. The left hand side will be the PCA, right hand side will be the LDA. That information I given to you. So from that information, can you understand what is the problem? What is the problem, or what is the difference, or what do you understand from these two diagrams?
Here classification is also happening. It's separating.
It's separating, right? So actually, if you see the left hand side, there also we are taking one projection vector. That is the eigenvector that we are discussing in PCA. So here also we are choosing one projection vector. Our objective is same. We have to find out the projection vector, but that projection vector should be keep the property of data set before applying that LDA or PCA. So if in the left hand side, if you take that blue color line, that is the projection vector. So when we choose a PCA simply choose a line. That line that the principal common axis, that when we are projecting all the data points to this blue color line, all the data are overlap each other. So you can see this. But now also the left hand side diagram, you can see this left hand side diagram. So that time now also there will be we reduce the dimension from 2 dimension to 1 dimension. But in the right hand side diagram, we can see this. There will be a 2 axis. We are choosing a random line, that is a projection vector. That actually in PCA and LDA, our purpose or objective is same, finding out the projection vector. But in PCA, what is we not bother about the classification property, whether the data having the classification property or not. We blindly go for a projection vector. But in LDA, what we are doing is we are also searching for a projection vector. But that projection vector should be make the classes before applying LDA. What is the property of the particular data points? Whether the particular data points belonging to 3 classes or 4 classes or 2 classes, we should keep the property. We should not reduce the property of the data points after doing this LDA. So LDA gives this advantage. So before we are having this the data, after the projection also the classes are separated. So you can see this right hand side diagram. This is the blue color line projection vector. In LDA we have got. So this is in the left hand side diagram, the blue color line we got in the PCA. So when we are applying PCA, we got this blue line. This is for imaginary purpose only. Actually, not exactly I'm telling. So if you say if I am applying PCA, I got this blue color line. This is the projection vector. After this projection vector, I'm projecting my data points to this line. Right? But what happened? All the green color circle, square and red color circles are overlap each other. After projecting, after reducing this 2 dimension to 1 dimension, I could not classify these two into 2 different separate classes. But in the right hand side and the right hand diagram, what happened? There will be 2 axes. We are having a 2 dimension. But when I applying LDA, when I projecting my data points to this LDA projection vector, this projection vector, when I applying LDA, that time my data points are classified same wise. So there is no problem. There is no overlapping and all. So this is the thing we are getting from LDA. But what is the problem? What is the difference between LDA and PCA is LDA is the supervised learning method, supervised dimensional detection. But in PCA is the unsupervised learning. What is the meaning of supervised and unsupervised? In supervised, we are know the label of the data. This data is belonging to particular class. This data is belonging to the particular class. But in unsupervised, we don't know that label of the data. So PCA is unsupervised one. So we don't know whether this green class square is separate label or red color label is separate label. We don't. The PCA does not know about that. So we are applying the PCA. The data, we cannot know the labels of the data. We are having the data. We apply the PCA. We reduce the dimension. But in LDA, we go for a supervised one because we know that these data points are belonging to this class 1. These data points are belonging to this class 2. We are having in our label, output label in our hand, in our data set. So we apply this LDA for that. So LDA for that, we keep that label not affected. So that is our purpose. This is LDA. Right, okay. So now we go for a Fisher's LDA. So LDA is a generalized form of Fisher's linear discriminant, right? Fisher is a person, he initially in 1936, he derived this thing, this discriminant function to classify between two plant species, Iris sectosa and Iris versicolor. So these are the two species, this is a binary class classification. 1936, he did the binary class classification using his discriminant function. So later on, this Fisher discriminant function has been generalized and it will be called as linear discriminant analysis. So that will be derived by C.R. Rao in 1948. He go for a multiple class. Hereafter, the concept is coming. Please listen carefully. So the basic idea of FLD, that is a Fisher linear discriminant, is to project the data points onto a line to maximize the between class scatter and minimize the within class scatter. Have you heard the word scatter? Before that, scatter matrix. Have you heard the word scatter matrix? Have you heard this word scatter matrix anywhere? No.
No, sir.
Okay. So actually, the scatter matrix is not a big new thing on all. So it is like a covariance matrix only. It is like a covariance matrix. Some places it will be called a scatter matrix. Some places it will be called as covariance matrix. So here, what we are doing is, so the basic idea of FLD is, so once again we are coming to deal with where we are going to deal with the covariance matrix. Keep it in your mind. So that only last class I have spent so much of effort and time for calculating covariance and matrix. And the basic idea of Fisher linear discriminant is to project the data points onto a line to maximize the between class scatter and minimize the within class scatter. Scatter, what is the basic meaning of scatter? Variation, scattering different data points are scattered in different in the plane or in the space or in the particular place in the different orientations. That is called scatter, right? So that is, or otherwise you can call it as variance, how much variability in the data. So particular class. So if in our given problem, there will be two classes, class 1 and class 2. So the class 1, the data points are belonging to the class 1. How much variability between these data points in the class 1? So how much variability among the data points in class 2? That is class 2 scatter. So this is called as within class scatter. Similarly, we have to find the between the class scatter. That is class 1 and class 2. The data points in class 1, data points in class 2. What is the variability between class 1 and class 2? That is called as between class scatter. So your purpose is your understanding is in FLD or in LDA, we have to calculate the between class scatter. So that is class 1 or class 2. So how many number of classes available in a particular given problem or a given data set? So we have to find out the two things. One is called as within class scatter matrix. Another one is called as between class scatter matrix. So we want to maximize the between class scatter matrix. What is the meaning of this? When we are maximizing the between class scatter matrix, these two classes are separated far away after the projection also. So if we find the between class scatter matrix, so our objective is to projection vector should make this between class scatter matrix maximum. So because we are going to choose the projection vector, we are randomly choose one line, and in the PCA, that the explanation I given for PCA. Similarly, here also there will be so many projection vectors are available. That is an eigenvector. So many projection vectors are available. We are going to locate one projection vector. That projection vector should maximize this between class scatter matrix, the distance between the class scatter matrix, and minimize the distance between the within class scatter matrix, not between within class scatter matrix. So this might sound a bit cryptic, but it's quite straightforward. So before delving deep into the derivation part, we need to get familiar with certain terms and expressions. So these the bolded lines, you should keep it in your mind, this word. So this is very important. The basic idea of FLD is to project data points onto a line to maximize the between class scatter and minimize the within class scatter.